Now in this video I will explain to you what is an electric field. Okay. Now suppose there is a charge here, okay, suppose there is a charge here, let us say it is some positive charge. Now if I keep a second charge here such that the distance between them is very large, infinite, then what will be the force on this charge? Force F is equal to K Q into this charge, whatever it is, let us call it Q dashed, divided by R squared. But R is how much? R is infinity. So if I substitute infinity, I will get this force will be equal to 0. That means if there is one charge here and if a second charge is very far away from it, the net force on that charge will be equal to 0. Now I am saying that if the second charge is very far, so now how far are we talking of? Suppose it is at some distance. So let us say it is at some distance d. Let us say the charge is here, this charge is here. Now will there be a force acting on it? Yeah. So what I am trying to tell you is, if there is a charge here, there is a 3-dimensional space around it where if you bring a second charge, it will experience a force. Beyond that, it will not experience a force. So that 3-dimensional space near a particular charge where a second charge will experience a force is called an electric field. Okay. So an electric field is a 3-dimensional space around a charge where a second charge will experience a force. So that region is called an electric field, and the question is how much force? How much force will a second charge experience? So that will depend upon the strength of the electric field. Now the strength of an electric field is defined as let us call it E, it is called E. E vector is equal to F divided by dq, limit dq tending to 0. That means if you bring a second charge which is called a test charge, and this test charge is necessarily positive. So if you bring a second positive charge, a unit charge close to the first one, the net force experienced by it is what is known as the strength of the electric field. So suppose this has a charge equal to Q dashed, F is equal to K Q dashed divided by R squared. But Q dash is a unit charge. Because it is a unit charge, I am going to remove it. Or if I look at the definition of an electric field, it will be equal to this force divided by Q dashed. So Q dashed will get cancelled. Then this value that you have here is what is known as the electric field or the strength of the electric field. Okay, or it is also called the electric field intensity. So the electric field intensity is equal to KQ by R squared. It is also called the force per unit charge. So its units will be newtons per coulomb. Okay, its units will be newtons per coulomb, and it gives me the force per unit charge. So if I have a charge Q here, if the electric field here is KQ by R squared, then if I bring a charge Q2, what will be the force? This is the force per unit charge. Because I am bringing Q2, the net force will now on this charge will become Q2 by R squared. That means force is equal to the second charge into the electric field intensity. Force is equal to Q2 into the electric field intensity. Now because force is a vector quantity, electric field intensity is also going to be a vector quantity, and the direction of the electric field at any point will be the direction of a positive charge placed at that point. So if I have a positive charge here, the electric field intensity will be in this direction. If I have a negative charge here, the electric field intensity will be in this direction. So it is because of this that if you see, if there is a negative charge, the field lines are all approaching it. So they say that a negative charge is a sink for electric field lines. These are imaginary lines, these imaginary lines are called the field lines. So the electric field lines are, the negative charge is a sink for electric field lines, and a positive charge is going to be a source for electric field lines. Okay. So, next what I will do is I will explain to you what an electric field line is, provided we are sure we understand this. Now, sometimes it may help you if you just pause the video and then try to rewrite or relook at the entire video from the beginning, then it will be helpful. So, if you look at the same thing 2-3 times, it will be helpful. So, the kind of question that you will get in your board exam is they can simply ask you what is electric field intensity. Okay. And there is another important question here. I said electric field intensity is F by dq, limit dq tending to 0. Now, why should dq tend to 0? So, a typical example that I would like to give is this. Suppose you have a book, your notebook, your paper. I crumpled the paper and you do not like it. You tell me that, sir, you please neat it and then give it back to me. So, if I have to make it flat, I can do two things. I can try to take it near a road roller and try to run the road roller on your paper. Alternatively, I can try to bring a hot iron box and then try to iron the paper with the iron box so that it becomes smooth again. Which of these will you use? Now, definitely you would not want to use a road roller, even though a road roller can be used to make things flat, but this is too small for it to make it flat. Likewise, when you want to find out the electric field intensity, suppose my charge is 10 power minus 6 coulomb and you bring a test charge which is 1 coulomb. So, this test charge is much bigger than the actual charge that you have. So, this is not the right thing. What will happen is the electric field of this test charge will influence the actual electric field. So, the measurement or whatever study you are doing will not be proper. So, to ensure that you are using appropriate charges, we have written that the test charge should tend to 0, and that tending to 0 will depend on what is the charge that you are considering. So, if you have a charge 10 power minus 6 and you want to study the electric field around it, you can bring a test charge which is, let us say, 10 power minus 12, it works. But you can't bring another charge which is 1 coulomb because that is much greater than this. So, that is why they have written here limit dq tending to 0. Yeah. So, I hope you understand. Number 1, electric field is a region around a charge where if you bring a second charge, it will experience a force. Second thing here, remember that electrostatic forces are non-directional. That means in all directions electrostatic forces will be the same. Yeah, in all directions electrostatic forces will be the same. So, wherever you bring the test charge, it will experience a force. That is why it is a 3-dimensional space. So, I told you about an electric field. An electric field is basically a 3-dimensional region around a charge where a second charge will experience a force. Now, an electric field can be shown diagrammatically or graphically by means of imaginary lines which are called field lines. Say for example, if you have a positive charge here, the field lines look like this. These are radial and they move in all directions. In case of a negative charge, the field lines look like this, they approach the charge. I already explained to you that this is the source for field lines, and I have explained to you that this is a sink for field lines. So, what I am trying to tell you is this, that one, understand that field lines are so drawn that if you keep another positive charge here, the force is in this direction, that is along the tangent. If you keep another positive charge here, the force will be in this direction. So, the force is in the direction of the arrow for what? If you keep a positive charge there. Similarly, if you keep a negative charge, if you keep a positive charge here, that positive charge will move towards the negative charge, implying that there is an attractive force. Okay. So, field lines are number 1, imaginary lines. 2, they are so drawn that the tangent to them will give you direction of force acting on a positive charge. Then 3, we can understand if you look at this here, that look, field lines are continuous lines. Okay, so here I have drawn the field lines for a positive charge and a negative charge separated by a distance. So, when they are separated by a distance, the field lines originate at positive and then terminate at the negative. So, this is a property of the field line, they will originate at positive charge, terminate at negative. Then you see in between they are continuous lines. I am not drawing field lines like this. So these are discontinuous lines. So field lines are not discontinuous lines, field lines are continuous lines. So here I have discontinuous lines. So these are not field lines, these are field lines. Okay. Now here I have drawn the field lines for two positive charges separated by a distance. Now please understand that if I keep a positive charge exactly in the middle, now this will push, because these two charges are the same, the net force on this is 0. So such a point is what I will call as a neutral point. So if you have two like charges separated by a distance, there will be some point in between them where the net force will be 0. If the net force is 0, there will not be any field lines passing through that point. So I have drawn my field line such that no field line is passing through this point. Then if I keep a positive charge here, this charge is going to push it in this direction. This charge, the second charge, would push it in this direction. As a consequence, the net push will be in this direction. So that is how the field lines are going. Okay. So these are the field lines which have been drawn where the field lines of one charge are being influenced by the field lines of the other charge. So this is how you would draw the field lines for two positive charges separated by distance, two equal positive charges separated by distance. This is how you will draw the field lines for two equal and two charges which are equal in magnitude but opposite in sign. Okay. So this is for a positive charge and a negative charge alone. So these are field lines. Two things, remember, if there is one field line here and if there is another field line here, two field lines cannot intersect. Why can they not intersect? Suppose I draw one field line like this, then this is the direction of the force on a charge here. If I have another field line like this will be the direction of force acting on the second charge. So now you see, on the same point, if I keep a charge, there will be a force in this direction and there will be a force in this direction, which is not possible. There can, at a point there can be only one direction for a force. So at a point there can be only one field line, two field lines can never intersect. Okay, so understand that, yeah.